Okay, so we stopped in the last recording. We were talking about zirconium monolithics. We discussed the zirconia block composition in details. We stopped here in the aging process or low temperature degradation, known as LTD. Low temperature degradation. Zirconia is susceptible to aging or so-called low temperature degradation, LTD. During this aging process, the metastable tetragonal phase converts by a slow transformation into the stable monoclinic phase, starting at the surface in the presence of water at relatively low temperatures, or in the presence of water or oral fluids or other fluids, because this we're not just talking now. Here in this lecture we're only talking about dental prosthesis, but like I pointed before, it's used in orthopedics for hip replacement or shoulder replacement or knee replacement. They use zirconia joints, so it's susceptible to low temperature degradation and matters to them, and we will touch upon that later in this lecture. So it's pretty much causes surface roughness by surface uplift in the presence of the oral fluids or bodily fluids. All right. Now, okay, that's an example. Hip and knee prosthesis. You know, it's a major surgery when they want to replace a knee or a hip joint. So they look at more than 10 years. They want something, the success rate to be above 10 years, obviously, because it's a major procedure. While I think in the dental field, 5 to 7 years success rate is okay. I will show studies that will talk about success rate for certain prostheses, PFMs and zirconia, up to 10 years, and there's up to 25 years study on PFMs as well. I will show all of that, but I wanted to point out that it's very important. Low temperature degradation is very important in orthopedics and as well as in the dental field. All right. Now, I was trying to find out, is there anything in the lab or in the clinic that we can do to reduce the risk of low temperature degradation? But all I found was this: strategies to reduce the risk of LTD, particle size reduction, and this is the manufacturing level. We can't control that in the lab. Increasing the anterior continent, same thing, it's a manufacturing level. Addition of aluminum oxide. Now, what did we talk about aluminum oxide in the last recording? In the third video, we talked about that when you add more aluminum oxide content, or the grain size of the aluminum oxide is bigger. So when you increase the aluminum oxide in size or amount, it will reduce translucency. But here we're discussing low temperature degradation. The addition of aluminum oxide is beneficial and it lowers low temperature degradation. All right. So when you add aluminum oxide, you reduce low temperature degradation, but you reduce translucency. So it has a good effect and a bad effect. Or let's say, when you look at one continent, you have to think about multiple things: the effect on low temperature degradation and the effect of translucency in the case of aluminum oxide. Same thing goes for tetragonal. When you think about tetragonal, you think about translucency. More tetragonal, less translucency, but more tetragonal means more strength. So one element will give you many effects on different aspects of zirconia behavior. All right. So addition of aluminum oxide will reduce low temperature degradation. Changing the chemical synthesis route to gain zirconium oxide raw particles. So as you can see, all these four factors are manufacturing factors. In the lab, there isn't. I was thinking about like double glazing or polishing, then glazing, whatever I can do to the surface to reduce the risk of low temperature degradation, but I didn't found any publication that supports that. All right. So it's all on the manufacturing level as far as I know. Now, machining can introduce stress or tension to the surface, which can enhance susceptibility to low temperature degradation. In other words, if it's printed, there is least chance or lower chance of low temperature degradation. But if it's machined or CAD-CAMmed or milled, then there is a higher risk of low temperature degradation, since there is stress and tension. It introduces stress and tension to the surface. And we will gonna be talking about printing zirconia. It's a newer thing that's coming up, and we will talk about it in details when we get to that part of the lecture. The same things, same talk about how to reduce low temperature degradation. Honestly, it's all about manufacturing in the lab and the clinic. I didn't find anything that we can do to reduce low temperature degradation. Same illustration, just to touch up on low temperature degradations. We're doing good in low temperature degradations in these generations that we use recently. Now, could we mix the particles of both deuterium, 3-deuterium tetragonal and 5-deuterium tetragonal, for example? In other words, we said that this block consists of many things: oxides, aluminum oxide, deuterium oxide, hafnium oxide, other oxides for coloring, and then there's the zirconium oxide in this block. So let's say that this block has 90%, for example, of zirconium oxide content. Of this 90% zirconium oxide content, can we use only 5-deuterium, or could it be a mix of 5-deuterium and 3-deuterium? Does it have to be one shape and form of the deuterium oxide, or could it be different shapes and forms of the deuterium oxide? Now here in the ZirCAD prime, evocolor evident mixed. All right. So in this step, the high strength zirconium oxide raw material, which is 3-deuterium as we established, and the high translucent zirconium oxide raw material, which is the 5-deuterium as we established, the highest translucent zirconium material, are combined in a special way. In a special way in multi-layering too. So you can say that the inner layer of this block, or the cervical middle third continent, is more of 3-deuterium tetragonal, and then the 5-deuterium tetragonal goes towards the incisal edges and the incisal 1/3. All right, and that would give you a nice degradation of strength and translucency. Heat element sintering versus microwave sintering. All right, there's a study that says it was revealed that the total sintering time was reduced by 75% for microwave sintering 3-deuterium stabilized zirconia ceramics to achieve relative density of 98% at low sintering temperatures. That's the key. If your block is centered at a low temperature, or a lower temperature than what I do, I center on 1450 up to the recommendation of the company that supplies me with blocks. So my blocks are centered on 1450. All right, but if your blocks are centered at a low centering temperature, about 1200 or 1250, then you can use microwave sintering. And microwave sintering would save you 75% of the time. In other words, instead of centering for 8 hours, you will center for a couple of hours. 2 hours is enough. 75% of the time you save. All right. However, the properties of both microwave sintering and conventional sintering sintered ceramics are comparable when the sintering temperature exceeds 1250 Celsius. In other words, if there's a block that's centered on a lower temperature, 1200, go ahead for the microwave sintering furnaces, because it will save you 75% of the time. All right. But as I indicated, most of our centered blocks in this region mostly comes from Germany, and mostly are centered between 1450 to 1550. All right, that's the range. I haven't seen a block that's centered on a low temperature, lower than 1200 or lower than 1200 Celsius. Now I put this study up because this is a PhD study for a doctor. He's called Muhammad Zahran. He did it in Toronto, Canada, 2014. I love it, so I put all these highlights and all kind of stuff just to show you that this is a very long study, 2019 pages. This is page 111. I have it in PDF. I've read it more than once and I highlighted much information I got out of this PhD study. It's really worth reading. It's really worth reading if you have the time and the patience to read all of that. But anyways, because he's talking about everything he wants to discuss, Dr. Muhammad, he brings previous studies. All right, he gathered previous studies and he discussed them, and then they would go ahead and do their own experiment and add it, and then compare it. Why is it different? Why is it a little different? Why is it too much different? What's the study limitations? How did they do it? What's the testing mechanism? It's just beautiful. It's something else. If you have the time to read this PhD study, it's worth reading, honestly. It says here in this part, this is what I want to quote from it now: the tetragonal crystals in these zirconium oxide ceramics are metastable and can be transformed into larger monolithic crystals with the application of stress from cracks or flaws. This phenomena is beneficial in hindering crack growth and increasing fracture toughness. Hence, it is referred to as transformation toughening. Transformation toughening is one phenomena that exists in zirconia. It doesn't exist in lithium disilicates or in other porcelains, especially for zirconia. Pretty much the conclusion of it, you have a tetragonal zirconia now, and there is a crack. This surface crack is trying to do a propagation, go inside the inner layers of the zirconia. This pressure from the tip of the crack will do this effect on the tetragonal zirconia. This tetragonal zirconia, by the effect of the head of the propagation crack, will transform to monoclinic, larger size shape of zirconia that we talked about, to monoclinic phase zirconia. This monoclinic phase zirconia has larger size particles, and it is capable of hindering or stopping the propagation mechanism. So it's a crack propagation stopping or hindering mechanism. It will stop the crack from going deeper inside of the deep layers of this zirconia. All right, so it's a good phenomena. It will stop, not heal or not close this crack. The crack is there and it will remain there, but it won't propagate more. It won't go inside the deeper layers of zirconia. And this phenomenon is called transformation toughening. Now, it doesn't exist in lithium disilicate or in other ceramics. I looked for that. It's a specific phenomena that exists in zirconia. Now, on the short term, let's say that this is really good, and it's a good phenomena, and it helps the zirconia, because in other products, once there is a crack, it keeps propagating until it breaks and causes the failure of that prosthesis. But this is a good thing in zirconia, transformation toughening. But in the other hand, don't forget that there is low temperature degradation. There is always cracks in the outer surface of zirconia. And these cracks, when they're multiple in the outer surface of zirconia, even if they cannot propagate inside of the zirconia, they would cause eventually failure of this zirconia outer layer or outer part. So that's why you see chipping of the zirconia, and you see more chipping in the outer zirconia. Now, we used to see failures between the bond of the ceramics bonded to the zirconium core too, and we will discuss that later. But here, this is a good phenomena on the short term. On the long term, we really have to take into consideration the low temperature degradation of the zirconia and the ultimate result of failure of this zirconia after many years. Now, how many years and how can we reduce that? It's all up to science and manufacturing to determine the composition of this block, and for the studies to come up with success rate for zirconia. I have one study that talks about success rate of zirconia for 10 years. I will illustrate that here. I will show that study here in this lecture as well. But it's good to know that there is a transformation and toughening in zirconium when it comes to hindering or stopping the crack propagation. Now, does this phenomenon exist in lithium disilicate? It does not. Is there an etchable zirconia? We will talk about this. This is just brainstorming again, but we will talk about this in its own part of this lecture later on. Etchable zirconia, we'll talk about that. All right. Now, since we talked about 7 different types of monolithics, we talked about alloy monolithics, we talked about acrylic monolithics, we talked about snap-on smile monolithics, we talked about high glass continent monolithics. That was number 4. Number 5 was composite resin monolithics. Then we talked about lithium disilicate was number 6, and number 7 was zirconia monolithics. We discussed these 7 kinds of monolithics. Now there is products in the market that you should try to know how to classify it. Is it like, let's look at this product for example. What is this product classification? Because it says zirconium oxide, it says lithium oxide, and it says silicate oxide. So what kind of product is that? Is it still lithium disilicate or zirconia, or what is it? Sometimes you see products in the market that you can't easily classify under which classification does it fall of the monolithics that we talked about. Now, flexural strength of this product, Vita Suprinity, is about 500 megapascal. All right, so it falls into the lithium disilicate strength or the lower zirconia strength. But let's look at the composition of this block, the Vita Suprinity. You see, that's the content of zirconia. Zirconium oxide is 8 to 12%, so very minimum composition of zirconia. Whether the lithium oxide, silicate oxide, so it's more of lithium disilicate or high silicate glass. But yes, they put lithium disilicate in there, 15-21% lithium disilicate, and they put a little bit of zirconia, say 10% of zirconia in that block. But at the end of the day, it's a lithium disilicate block. That's what I want to tell you. So you would see that some products are infiltrated with zirconia, or infiltrated with glass, or infiltrated with other components. But at the end of the day, what's the cluster and what's the matrix and what's the major component of that block would make the difference really. So can we enforce glass ceramics with zirconia particles? Yes, we can. Can we mix lithium disilicate with zirconia? Now, we're not talking about infiltration. We're talking about, say, 50-50 mix, or 40-60 mix, whatever. Can we really mix zirconia and lithium disilicate? And why would you even think about mixing such two different materials together? The answer would be you would hope that mixing lithium disilicate will give you the etchability and the glass and the high translucent of the lithium disilicate, and that the zirconia would give you the strength of zirconia, and can we mix it together or not? Now, there is a study by Dr. Zhu Yang. You know, the very short outcome, because it's really a long study that's really complicated for a person like me. It's too much chemistry, as simple as that. So GZ G offers better resistance to immediate flux or damage, better aesthetics, and potentially better veneering and cementation properties over homogeneous zirconium oxide deuterium stabilized zirconium. So what does this mean? The conclusion was using a combined glass infiltration densification technique, GZG, with a graded structure can be fabricated. So Dr. Zhu Yang proved that it can be fabricated. I don't know of any block or any final product in the market that was made with this technology, but at least it's proved that it can be done. All right. It offers better resistance to immediate fluctuous damage, better aesthetics, and potentially better veneering and cementation properties over homogeneous deuterium stabilized zirconium oxide. All right. Now this is Dr. Yu Zhang from New York University College of Dentistry, and he was awarded nearly 3.7 million by National Institute of Dental and Craniofacial Research to carry on with his researches. If you Google on Google Scholar Dr. Yu Zhang, you will find much publications and scientific papers that talk about dental materials and materials in general. It's just it's a lot, and it's beneficial. Actually, I have benefited a lot from the papers of Dr. Zhu Yang, as well as Dr. Edward McLaren and others, and all institutes, many institutes that publish their vision of work. I have benefited from, actually. But anyways, so going back, so you can have, or it's Dr. Yu Zhang proved that you can mix lithium disilicate with zirconium. It's possible, it's doable, it's manufacturable, as if that's a term. You can manufacture something, a mix, but it's a complicated process. It has infiltration and densification, and it's a complicated process to come up with, say, I don't know, a block or a powder or injectable, some form of material that is a mixture of both lithium disilicate and zirconia, and gives you both properties for cementation, translucency, and strength. All right, so that would be a breakthrough if it comes out. Imagine just not having to choose between lithium disilicate and zirconia anymore. Just use one block that works for all. It's amazing. Okay, now there isn't anything really that's called monolithic abutments, but I put it up anyways because we're talking about monolithic, and some abutments are prefabricated abutments, castable abutments, all kind of abutments we can discuss in this section. It's not really a part of monolithic versus layered lecture, but I said I'll put it up anyway. Monolithic abutments, just to see what kind of abutments do we have, and if we want to apply a classification of monolithic and layered, which does not really apply, but if we want to think about this classification in relation to abutments. All right, so this is a slide that I come up with. Abutment selection. Say that you got an indirect implant impression, a post analog, and a model port. Now you have a model. In this model there is an analog. Now you are up to the abutment selection, right? You want to select your abutment. What choices do you have? First of all, there's the transfer abutment, which is the abutment that transfer the relationship from the impression to your cast, and you can use this transfer abutment, cut the transfer part of it, the top part of it, and then the remaining is your abutment. You use it as an abutment, so it's a transfer and an abutment at the same time. Other kind would be preformed abutments. The preformed abutments, we always have to discuss the size, and us dental technicians refer to size. What's the size of this abutment? Well, size could be many things. Size could be, you should when you say size, you should think of three things: diameter, right? 5.0, 3.5, 3.0, 4.5, whatever, 4.0. So there's a diameter of that abutment, and there is cuff size, which is the height between the upper rim of the abutment itself, the analog in your model, and the margin line of that abutment, the neck, all right, the neck of the abutment, the cuff size. And then there is the coronal length. Some companies give you coronal length as an option. Like you can choose 2 millimeter cuff size and 5 millimeter coronal length for like deep or high prosthesis, long prosthesis, all right? And most companies don't give you coronal length. You just choose the diameter and the cuff size when it comes to preformed abutments. Now, that's talking about the size, diameter, cuff size, coronal length. Then you should discuss angulation, the angulation of that abutment. You know its diameter 4.0, you know the cuff size is 2 millimeter, for example, the coronal length is set, for example. You know the angulation 15%, 25%. And there is abutment material, and you should say a zircon abutment of 4.0 diameter within a 15-degree angulation, or a titanium abutment. So there's titanium abutment and there's zircon abutments, and I think there's a third kind of abutments that was produced. I forgot the composition. It's some kind of oxide. It's an element. It's not an alloy. It's an element, but I can't remember right now. If I remember, I'll put it in the comments. Anyways, castable abutments. There's two kind of castable abutments. There's the gold adapted UCLA, you know, University of California, Los Angeles invented this type of abutments, UCLA, the gold adapted that you can cast. It comes with a prefabricated hex with a plastic part on top of it, so you can play with the plastic. You can cut it, chop it off, you can add to it wax on top of it, do whatever you want, and then cast them, and then they become a one piece. But it's pretty much multi-layered. It's more than one layer, and you've fused it together. Okay, and then there is the fully monolithic or the full plastic abutment, and I will show photos of that. It's I was surprised that many people don't know about it, but we use it. We periodically use this full plastic abutment. The whole thing is a plastic, even the hex. All right, and you cast the whole thing as one piece of whatever alloy you want. And there's a custom mill abutment, of course, the CAD/CAM, the MCAD/CAM software in our machine. You just download it or upgrade to it, and then it'll be able to mill custom abutments or custom mill abutments from chrome cobalt or whatever have you. All right, and these custom mill, they come CAD/CAM for titanium and zirconia, as we said, and they come hand piece mill abutment. These are annoying. They're big and you have to grind the hell out of them, and it takes too much time to grind them. But it's a kind of abutments. Now there is other kinds of abutments, like a multi-unit that we use. You know, the multi-unit abutments. They're good solutions, especially for screw retained prosthesis. But anyway, I just want you to see how much of a selection there is for choosing one abutment. You know, for a single case, you have many options, and sometimes it's overwhelming. But once you understand how much of a selection you have and what can you do with it, it gets easier. So in other words, this is the old way of CAD/CAM, the old way we used to do this design. We used to send the cast, and then Astratic, they do the design and we approve it, and then they mill for us the abutments. Anyways, this is the newer ExoCAD techniques. It's just cases with, you know, designed, you know, how you choose the angulation and everything. It was all straight. This case, this is UCLA gold adapted abutment, casted, just a split technique zirconia abutment. Those are the milled abutments, CAD/CAM or handpiece milled. Another technique of just applying opaque under on top of the abutment, you know, and bake it to mask the grayish or the blackness of the abutment. Now this, I want to discuss this with you I think Straumann do have this box too, but this box is from Aniridge, from Megagen. I use Megagen. It's a Korean implant company, and I like this box because this box has 16 compartment times 3. Each compartment, for example, the first compartment is straight, the second compartment is 15 degrees angled, the third compartment is 25 degrees angled. In each compartment, like I said, there is 16 different abutments that you can pick and choose. They're all plastic. They're just for your own selection to know what to select, what best to select for any case. For example, for this case, we manufacture the CAD/CAM lower full arch temporary material, okay, on temporary abutments. The doctor had temporarily cemented this lower. Of course, this is the lower part of the articulator, but it's inverted. That's why you see the lower as a top, but this is the lower part. And then we did a final zirconia bridges on the 8 abutments, on the 8 abutments on the upper jaw. All right. So this was final, the upper was final. So for me to choose the abutments here, the final abutments, I have this box. So you pick and choose the height of the collar, the diameter, the depth, which is the height, the kind of the coronal length, and everything. All right. So you can only call the doctor. You can simply call the doctor and tell them, I want number 6 red 1, number 6 purple, for example, or pink 1, number 6, number 5 red 2, and you know, if you have the abutment, you can pick and choose the abutment itself too, you know. So anyway, instead of having big confusion about what to choose, what abutments works better, you can try all of them, you know, or most of them, and see whatever suits this case as the ultimate selection, the best selection, and then just call the doctor and order, or call the company and order specifically these, because sometimes we really have a hard time. You call the company, tell you, do you think you need angulated? You said, yeah, I think I need angulated. They would go, you think you need 15 or 25? I'm like, I'm not sure. Send both and I'll ship it back to you if it doesn't work, or send the you know, it's just, this makes selection very, very easy. If you buy this box for one time and you use the same of course, this only works with Megagen. If you want something that works with Straumann or with Noble Biocare or with other companies, Implant Direct, whatever have you, of course, I would assume that they have a different box and a different color coding and a different cuff sizes and everything for your cases. But it was a big help. Anyway, we talked about monolithic abutments. These are the plastic abutments from CWM, another Korean company that we use here in the Middle East a lot. It's fully castable, it's unthreaded from inside, and it has hex and everything, and then you just cast it. This case, for example, I had a UCLA and I had a fully plastic castable. You cast both, you know, put the margin line where it goes. Here is the castable in a different view. You know, you put your margin the way you want. You can make it wide, you can make it narrow, you can do whatever you want, and that's a casted hex. Well, of course, anything casted, the snug fit or the fit of it is not as precise and as snug as the prefabricated, of course. And that's one positive thing about using UCLA, because it's prefabricated hex. The connection with the hex is perfect fit. It's just snug fit. With the casted, you will feel that there is a fit and everything is fine, but I guess nothing casted gives you the same exact fit as prefabricated. So usually we use it like this. You don't depend on it by itself. You usually use it with castable, with UCLA castable abutments. Like say that we have 4 or 5 implants and it's a 1 unit bridge prosthesis that will be fabricated on top of it. You choose some of it the extreme angulation, okay, you can use it from this kind, which is the fully castable plastic, but you have to include, or it's better that you include UCLAs for a good fit, of the hex. So anyway, I get them used I get them mixed most of the times, not this by itself, but a mix of UCLA and a fully castable. That's for especially for larger cases. Anyway, that was for monolithic abutments. Now we can talk about handling for a little bit. Or actually, this is a 35-minute video. I think I should stop right now and talk about monolithic prosthesis handling, whether it's alloy monolithics or zirconia or lithium disilicates. We will talk about monolithic prosthesis handling in the next recording. That was the seal of my 4th video. Thank you for watching.